In earlier videos, we came up with a cost function for linear regression, and then we derived the gradient descent algorithm for trying to minimize the cost function. Now let's apply the gradient descent algorithm to that cost function and figure out a specific algorithm for implementing linear regression. And by the end of this video, you know how to implement linear regression using gradient descent. Let's recap what we saw previously. We said that the gradient descent algorithm is an algorithm for minimizing a function, and what it does is it repeatedly updates the parameters theta j via this formula where alpha is the learning rate. Okay, and you do this until convergence. And we also said that for linear regression, we have a cost function j of theta, which we defined as that, a sum over my training set of this squared error term between what my hypothesis using parameters theta outputs and what was the actual observed value. And we defined this saying that h of x is equal to theta transpose x, or equivalently is a sum from j equals 0 to n of theta j xj. What I'd like to do is take these two pieces and put them together to apply the gradient descent algorithm to minimizing this cost function j of theta that we've defined here. And in order to apply gradient descent to this, the key term we need to figure out is what is this partial derivative term, and we need to figure out what this term in the blue box is, so we can plug that in here and implement gradient descent. So the partial derivative term we need to figure out is what's the partial derivative with respect to theta j of theta, and we can rewrite that as follows. I'm just plugging in here, I'm just plugging in the definition of my cost function j of theta. And again, to simplify, or if I plug in the definition of h of x, that's just equal to this, to m, so that's theta transpose x minus yi, theta transpose xi, like so. Okay, and let's see. So this is the partial derivative with respect to theta j of this term on the right, and computing this partial derivative requires a little bit of multivariate calculus. And I'm not going to do the derivation, but if you actually figure out what this derivation is, it turns out you end up with this term. I'm just going to write out the answer here. Times x I j. Okay, so this term here is equal to what happens if you take this, compute this partial derivative. If you're familiar with calculus or with multivariate calculus, please by all means feel free or feel encouraged to go through this derivation and try to prove this result yourself. In some later videos, I'll say a bit more about the math behind linear regression, but if you're unable, or if you don't remember that much calculus, or if you don't, you actually don't need to go through this derivation yourself, you can just use the right answer here, which I've already derived for you. So going back to this equation, here's my partial derivative, and thus this gives me my gradient descent algorithm, which is, I'm going to repeat, update theta j as theta j minus my learning rate times that term, minus yi times x I j. Where of course this is just that partial derivative term that we worked out just now. And you perform this update simultaneously for all j, meaning you do this update for theta 0, theta 1, theta 2, and so on up to theta n, where n is the number of features as usual. Okay? So let's see how this gradient descent algorithm works when we apply it to linear regression. When I explained linear regression, we saw this picture, and we saw that depending on where you initialize gradient descent, it can converge to different local optima. It turns out, fortunately, that when you look at the cost function j of theta for linear regression, this turns out not to be the case for linear regression. And in particular, rather than this sort of bumpy function, the cost function j of theta for linear regression always looks like a big bow-shaped function like this, which you can see that this big bow-shaped function has only one global optimum down here at the bottom. And this turns out that for any data set you have, for any training set, for any set of any number of parameters, theta 0, any number of features, the cost function for linear regression is always this sort of bow-shaped function with only one global optimum and no other local optimum. Let me take this function and replot this function using the contours. It turns out the contours of the cost function j of theta is going to be look like this. So this is the contours of j of theta, and the global minimum of this function is this point down here, right? That is denoted by a little red cross. And so these are the contours of concentric ellipses, the contours. Now let's say I initialize gradient descent using say at this point out here, right? Let's denote that with a red arrow, and so this is my initial value for theta 0 and theta 1. Let's say I now take one step of gradient descent. What happens? Well, one step of gradient descent will move me like so. And I'm now at this new point over here. Take a second step of gradient descent. That's after 2 steps. Now I'm going to take another step, 3 steps of gradient descent, 4 steps, 5 steps, and so on until gradient descent converges. And it does indeed converge to the global optimum. And so this is what gradient descent for linear regression looks like. To look at this in a different view, here's my training set with my 47 houses with price on the vertical axis and size on the horizontal axis. So let's say I initialize my parameters at 0, 0. Then my hypothesis, or the housing prices I'm going to predict, is going to be a flat horizontal function, right? So this is flat blue line that I've just placed at the bottom. And this flat blue line, it corresponds to the hypothesis, h of x equals 0 plus 0x. So this is if theta 0 is initialized to 0 and theta 1 is initialized also to 0. It just predicts all houses are free. After one iteration of gradient descent, you end up with a new value of theta 0 and theta 1, and turns out you end up with this line. And slightly better fit to the data. And after 2 iterations of gradient descent, you end up with this. After 3 iterations, 4 iterations, 5 iterations, and so on, until it converges to this straight line, which is a reasonable fit to the data. And it turns out that the specific parameters it converges to on this data set are, h subscript theta of x equals 71.3, plus 0.135 times x. And so it's saying that each additional square foot costs about another $0.135 thousand dollars, or $135 per square foot, but on top of that, a house of size 0, which doesn't really exist, costs about $71K. So this is our model for the price of a house. So that was the gradient descent algorithm. Just a few more comments on this. To give this another name, this algorithm is sometimes called batch gradient descent instead of just gradient descent. And the term batch is not a great name. Don't worry too much about what, again, batch means, but it captures the intuition that this algorithm looks at all the training examples at the same time. Right, so each iteration of gradient descent, computes the partial derivative with respect to j of theta, and j of theta was defined using the entire training example, right? And so the term batch captures the intuition that we look at all of the entire batch of all training examples. It's not a great name, but just this algorithm, treating all the training examples as a batch. It's just another name for this algorithm. It turns out in later videos we'll describe a different version of gradient descent that looks at only one training example at a time rather than all the training examples, and that other version, which I won't talk about later, sometimes works better on very large data sets and in a few other settings. But for now, just if someone says batch gradient descent, it means exactly this algorithm that we talked about. And hopefully, having watched this far, you now know how to implement batch gradient descent, and you'll be able to get this to work on linear regression yourself. To wrap up this video, I want to close with a quick, I have a question for you, which is, earlier I said that gradient descent will converge to the global optimum for linear regression. And so why is that? Is it because we slowly decrease alpha, or is it because it converges, or is the reason that it always converges to the global optimum? Is it because it converges even for fixed alpha? Or is it because it's always guaranteed to find a global minimum? Or is it because JF theta has no local minimum? So hopefully you got that this fourth choice is the right answer, and in particular, first answer is just wrong, right? We actually do not need to decrease alpha so that gradient descent converges. And let's see, it is true that gradient descent will usually converge even for fixed alpha, but this is not the reason. This is true even for functions where they're local optima. So this isn't a reason for the statement above. And gradient descent is definitely not guaranteed to find the global minimum of any function. It can get stuck in local optima. But instead is that the specific form of cost function j of theta we define for linear regression is always this sort of big bowl-shaped function that, and this is a property of j of theta as defined in linear regression. And so, this fourth choice is the answer for, is the reason why why gradient descent always converges to the global optimum for linear regression. And that wraps up this video, and using this, I hope you'll be able to implement gradient descent and linear regression for your own problems.